Hello everyone! Today I want to tell you about a Rabin-Karp algorithm. Let's start from the general explanation of this algorithm. Well, in computer science, Rabin-Karp algorithm is a string searching algorithm created by Richard Karp and Michael Rabin in 1987. It uses hashing to find an exact match of a pattern string in a text. And here is some words of creators of this algorithm. There is a bunch of text, so I don't want to read it full, you may do it by yourself. But I just want to emphasize one important thing about this statement. Algorithms require a constant number of storage locations. What does it mean? It means that the space complexity of this algorithm is the constant. We don't allocate any extension memory to proceed the algorithm, and it's really good. And as we start talking about the complexity, let's talk about time complexity, which also important. It's probably one of the main characteristics of any algorithm. And here is my calculations of this complexity, of this time complexity. So here we can see that the best case is O of n plus m, whereas the worst case is O of n times m. And here we can see why it works. So a bit later I will show you another improvement which probably will be more understandable for you, but it depends on you. Let's go next. And let's talk about the main concepts of this algorithm. As I said previously, it uses hash function, but it uses a rolling hash to quickly filter out positions of the text that cannot match the pattern, and then checks for match at the remaining positions. Generalizations of the same idea can be used to find more than one match of a single pattern, or to find matches for more than one pattern. We will talk about this a bit later. And what gives us using rolling hash? What does it mean? Well, it means that calculations of the next string's hashes will be based on previous hashes. And it makes hash finding algorithm working so quickly. It takes all of one time. It takes constant time, which is great. But anyway, I have to emphasize this fact that we spent all of m time to calculate the very first hash. All the other hashes will be calculated for constant time, and it's still great. It's still awesome. And here's some visualization of this algorithm. For example, we have string a, b, c, d, e, f, g, h, I, j, k, sorry. And a substring we need to find e, f, g, h. We choose a big prime number. Let it be 5. Not so big, but still prime and still good for this data. Okay, so what do we need? We need at first to calculate the hash for substring we need to find. And here is the polynomial or rolling hash, whereas 101, 102 is Unicode code of letters, of charts. We get a number, 15,794. What do we do then? Then we calculate hash for the very first substring with length 4. This is ABCD obviously. And we see that the hash of this substring doesn't equal to the ones we need to find. And what does that mean? What does it mean in terms of hash function and string comparisons? We know that if hashes are same, it doesn't mean that strings will be also same because of collisions. You know, it's very terrible stuff. But there is really interesting moment that same strings has same hashes. Same strings has. Let's go. Come on. Same strings same strings have same hash functions. Let's reconstruct this phrase. different hashes means that the strings are also different, and that is good. So we have different hashes. That means different strings, and we skip it. Let's go on. We shift we shift our border of our window of length 4 to another substring, which is B, C, D, E. Again, we calculate hash, and we can see that this hash is also it doesn't equal to our hash string we need to find. We go on the next substring C, D, E, F. What's the result of hash? Oh, so sad. So close, but no, it doesn't satisfy us. Go on. The next substring, much more closer, but still we didn't get an appropriate number. Maybe this substring will give us the correct hash we need to find. Let's check it. Oh, let's go. We've just got the hash we need. 15,794. And surprisingly, these hashes belong to the same string which we need to find. But generally after that, after we got same hashes, we need to compare strings anyway because of collisions. I said about this a few minutes before. But as we can see, these strings are absolutely equal, and the algorithm returns the index of first occurrence of string we need to find. It returns 0, 1, 2, 3, 4. It returns 4. That is the end of this algorithm. I think with having visualization, this a bit clarified some important things about this algorithm, some moments that you may not understand before, but now I hope you understand this algorithm. So we may move on. Let's talk about my favorite part, graphics. Here we can see time dependency of two different implementations of this algorithm, least one and array. I calculated the time in milliseconds. So what can we see? First of all, the red line belongs to list, and the blue one belongs to array. And what can we see? We see that list implementation is much slower than array one because its function grows dramatically faster in comparison with array one. But actually, if we're talking about the time complexity, uh, so calculating of time complexity doesn't use time in its real understanding. We don't use milliseconds or seconds to calculate the time complexity. No, we don't use it. So this graphic is quite subjective because real time milliseconds depends not only of how the algorithm was implemented. No. It also depends on many factors of your processor, of your machine. So let's take a glimpse to another graphic. This one. This graphic shows us iterations dependence of two different implementations, list and array as well. The purple line is list. The red line is array. There we can see that they're pretty same, but this information is much better. is much objective. But we have to divide these two graphics because we can approximately say that the least implementation looks like n squared probably, but in comparison with least we can't say absolutely nothing. We can say absolutely nothing about an array because it looks like a constant time, but it's totally wrong. Of course, now array implementations doesn't take constant time because it's impossible. It's impossible. So let's divide these graphics into. Here's the first. As I said, list implementation is quite close to the n square. So it means that the time complexity of list implementation is n squared. I think it's pretty clear. Let's go. And here's my favorite one, array implementation. In comparison with n plus m function, where n is the length of string, m is the length of substring. So we get completely same graphics. I mean asymptotically. Asymptotically they are same. They're growing in the same way. And what does it mean in terms of iteration and in terms of time complexity? It means that array implementation has really good time complexity, O of n plus m, which is equal to my previous calculations, which I have shown you a few minutes before. And what do we know about the strings? The strings, in some way we can call it an array of chars. And if we're talking about the complexity, we can do this. So we can do this. Okay. So that is the end of theoretical part, of mathematical part. It's sometimes kind of boring, but it ends. So, and let's back to practical use of Rabin-Karp algorithm. Well, a practical application of the algorithm is selective plagiarism. Given source material, the algorithm can rapidly search through a paper for instances or sentences from the source material, ignoring details such as case and punctuation. And because of the abundance of the sought strings, single string searching algorithms are impractical. That is a really huge advantage of Rabin-Karp algorithm in comparison with other one like Knut Morris Pratt, Boyer Moore, and other string searching algorithm. But algorithm which I'm describing now has disadvantage, of course. Of course, it has. Well, it's inferior for single pattern searching to other faster single pattern string searching algorithms because of its slow worst case behavior. I mentioned to you that it has O of n times n time complexity in worst case. It's a bit terrible, but what can we do with it? However, it's a useful algorithm for multiple pattern search. To find any of a large number, say k for example, fixed length patterns in a text, a simple variant of the Rabin-Karp algorithm uses a set data structure to check whether the hash of a given string belongs to a set of hash values of patterns we are looking for. It's great, it's great. To clarify this statement, I would like just to simplify it a bit. So we have the common implementation of Rabin-Karp algorithm, and instead of substring, we need to find. We have a set, like hash set or hash table, depends on programming language you use. This set contains all the patterns, all the hashes, and instead of checking whether the current hash is equal to the ones we need to find, we just We just check whether the current hash contains in the hash table or hash set. If it is true, we just add the results. That is great. Oh, I said there won't be any math, but I was liar. Yes, I bit forgot about this table, and not the table with random numbers, but they're not so random. Okay, so what can we see there? Uh, I think it's the same dependency as we've seen on my graphics, but it's just a table, and there we can see the time and iteration dependency of compared with the size. You can see that array start working faster from the very beginning, from the very small sizes like 1000 up to 10,000. The time isn't growing so fast, and iterations as well. But if we talk about linked list, there is a kind of bad situation. We have 4 milliseconds for 1000, 14 for 2000, and so on. And we spent almost 1/3 of a second to calculate to find substring in a string with length of 10,000. And we spent numerous iterations. I don't want to spell this number. You can see it by yourself. That is the end. That is the end of the presentation. And now let's look at the implementation of this algorithm. The main part of my video is of course implementation. How did I do this? Here's my class program with the main method. The first line, I'm just generating files of data, like files with 100 chars, 200, up to 10,000. Here's some list of tuples, of array of tuples. It's kind of difficult to understand why do I use this, but I needed to visualization. I needed to create a graphic, to create graphics, this algorithm, you know. In these two loops, we actually proceed the algorithm many times. So let's say it's 5,000 times. So the program doesn't work so fast. It takes like 10 minutes to proceed to get all meanings we want. Here we're creating visualization itself, some methods I used to create graphics. Nothing interesting. Let's better talk about the algorithm implementation itself. So here's the algorithm, the main part of my video, the algorithm. So what do we have there? We have an indexable of char. It's a source. Let's say it's a string. This means string. You don't have to be bothered with this line. It's just a string. Let's say it's string. And here's another string. Another string, which we need to find. The string which we need to find. So while algorithm proceeding, I'm also calculating the iterations and the time in milliseconds, of course. So let's start. First of all, we calculate the hash of string we need to find. Here's this line. And how do I do this? I've already mentioned that I use polynomial rolling hash. And let's take a glimpse to its implementation. Here we can see big prime number, another much bigger prime number, some variables, and the method itself, get hash code. Mm, just don't know how to describe it. I think you probably understand how does it work, because here we're just creating the polynomial itself, and using modulus, just to avoid overflow of integer numbers. After this calculation, we may get a big number, which is the hash of string we need to find. After that, we calculate the same way hash of the very first substring with length m, and we finally start our loop, which consists of n minus m steps plus 1, incrementing the count of iterations, and then we compare two hashes given there. If they equal to each other, we are checking for total equivalent of the string. We compare the string char by char, spending all of n time, and returning the value. Because of my task, I return not only the value, not only the string, and not only the index. I return also the time and the iteration my algorithm has spent to be done. Well, if two hashes don't equal, we don't worry about that. We go next, and here we updating our hash. Updating hash takes us just constant sum, as I said previously many times. Let's take a glimpse. Let's look at the implementation of the hash code. So it takes our alt hash and the first and the last chars, the first and the last letters of our string. We actually don't need to take full string. We just need to have first and the last one. The first and the last chars of the string. And here we're calculating. We just subtract the highest prime, multiply by first char, then multiply by prime plus last letter. All the operations are doing under the module. After that, we return given hash. That is the end of this loop. We do these operations n minus m times. Or we can do this a bit less if these hash and hash to find are equal. If they equal, we just check this equalization and return the value. That's how this algorithm works. And probably that is the end of my video. Thanks for watching. I hope you enjoyed time you spent with me, and see you later. Goodbye.